Thank you very much. I'm very happy to be here and give these talks. In my talks, this first talk, I just want to discuss some generalities regarding Galois cohomology of the maximal extension of a global field unramified outside a set of primes, a continuous Galois cohomology. In the second talk, slightly different from the abstracts, I want to discuss some various things about cyclotomic fields, class groups, and units, and then discuss the homology of modular curves and a relationship between the two. And in the third talk, I will discuss some conjectures. Well, actually, throughout each talk, there'll be, the second and the third, there'll be some conjectures of mine and some work of Fukaya Kato on those. Okay, right. So let's let P be a prime, and F will be some global field of characteristic not P. So, for instance, a number field. S is going to be a finite set of primes of S that containing F of F containing any primes over P in any real places. Of course, if it's a function field, there will be no such primes. Containing any primes over P and all real places. Okay, so by primes I mean places. Okay, so now the GFS will be used to denote the Galois group of the maximal extension of F unramified outside S, which I will call the maximal S ramified. So S ramified, meaning unramified outside S, extension of F. So this is a Galois group over F. If V is in S, then GFV will be the absolute Galois group of the completion of F at V. So in other words, the Galois group of a separable closure of FV over FV.
How is the real places when F is a field?
Right. So when F is a field of characteristic of non-zero characteristic, then there are no real places. So then there's no condition. Yeah. Yeah. And there's no places above P either. Yeah. There's no condition. Yeah. Okay. So right. So now I want to talk about Galois cohomology, but I want to take coefficients usually when you do Galois cohomology, you take coefficients in some discrete module for your Galois group, and the cochains are continuous cochains for the action on that discrete module. So continuous maps from some number of copies of the group to the discrete module. So continuous Galois cohomology, you may have, for instance, a finite rank ZP module, or more generally some compact module, and you just want to take those cochains to be continuous. Okay, so let's say that G is a profinite group. And T will be a compact Hausdorff, everything will be Hausdorff. ZP double bracket G module. So, so here this is the inverse limit of the group rings ZP G mod n, where n is normal in G and n is open. Okay, so equivalently, or T is a compact ZP module with a continuous commuting action of G. So this is equivalently. Okay, so so actually any such module is pro-finite. So in fact it's an inverse limit of finite ZPG modules. So so then T is isomorphic to an inverse limit of T alpha, where T alpha is a finite ZPG module, which has the discrete topology. Okay. So now I can consider continuous cohomology. So cohomology given by cochain complexes with continuous cochains. So continuous cochain complexes give rise to cohomology groups HI, GT, which I won't, normally maybe you would write sub CTS or something here, continuous, but I'll just write it as this. So this is a continuous cohomology. And it takes short exact sequences to long exact sequences and so forth. And so you could apply this with G being either any of these groups here. Okay, so let me give you some examples. So for example, if I take H1 of the maximal unramified outside S extension with coefficients in ZP1, so that is actually, so, oh, I should have said that, right? So let me just erase this. So HI GT is actually isomorphic to the inverse limit of the HI GT alphas, where T alpha are below. Okay. So so in the example I wanted to give, if I take H1 GFS ZP1, then that is isomorphic to the inverse limit of the same thing with mu pn coefficients. Well, it turns out, at least in the, so by Kummer theory, this group contains a subgroup which is isomorphic to the units in the ring of S integers of F modulo nth powers. When you go to the inverse limit, that's all that survives. So this group is actually, so this inverse limit is actually isomorphic to what I'll call EF, which is the P completion of the units in the ring of integers where I invert the primes in S, which, right. So that's what it is. Okay. In other words, S units. Okay. So OF, string of integers. I'll skip a discussion of H2 for now and talk about, well, what happens for the local places, which is maybe a bit easier than what I just described. So H1 GFV ZP1 is isomorphic to an inverse limit. Now it's the absolute Galois group, so the H1 of the with mu pn coefficients gives me this, and so this will be I'll just call this, I'll just put a p here to mean the p completion of the multiplicative group of FV cross. And H2 again is going to be an inverse limit of the p to the n torsion in the Brouwer group. So this will be ZP if V is non-Archimedean, Z mod 2Z if P equals 2 and V is real, and 0 otherwise. Okay, so I wanted to denote this E. Well, maybe that's fine. EF. I'll just call it EF, but it depends on S. Okay, so more generally, for any so for local fields we have, right? So we have Tate duality. So for any compact module, its Pontryagin dual is a discrete module, direct limit of finite modules. So T upper V is the continuous homomorphisms from T to QP mod ZP, and this is a discrete ZP GFS or G module. This is in general. So
Romyar, the inverse limit for the H2 with P equals 2 V real, the 2 torsion is Z mod 2.
right, they're all Z mod 2. Right, the 2 torsion, the 4 torsion, and so forth, and the maps are just the identity maps. So in the inverse limit,
They are the identity maps? They're not multiplication. They're not multiplication.
no, they're identity maps. Co-restriction is a surjective map because it's cohomological dimension 2.
Okay.
So, yeah.
Then it's strange because the other ones
The other ones, yeah, are ZPs.
are these pieces.
Yeah.
So they're different.
Yeah.
Two cases.
Yeah.
Okay.
Yeah. So, okay, so Tate duality says that if I have, so now I have my T is a compact ZP GFV module. Then Tate duality says that HI GFV with coefficients, so I should now take V is non-Archimedean. Otherwise I have to modify this. Okay, for the real places. So, so this HI is isomorphic to H2 minus I GFV. Now you take coefficients in the Tate twist of the Pontryagin dual, and then it's dual to that. Okay? And so that's always true. So now this is the usual Galois cohomology, right, with a discrete module there. And this is going to be given by some sort of cup product, which I'll discuss later. If V is real, you actually get a similar isomorphism, but you have to take Tate cohomology groups here instead of instead of usual cohomology groups. So now let's take the more complicated case. So let's suppose now that T is a compact ZP-GFS module. Then we have the Poitou-Tate sequence. Which is a bit long to write out. We'll see how I do. So there's a 9-term exact sequence. That goes like this. So global cohomology goes to local cohomology, goes to some sort of dual. So in this case of global cohomology. So I take the same thing, the Tate twist of the Pontryagin dual. I take the cohomology and I take the dual. And then I have the same group here, but with H1. And then the same local thing. Oh, this should be a V here. Okay, G, F, V, T. H1 now here. And then finally H2. H0. So these numbers go down while the others go up. Okay, so that's the Poitou-Tate sequence, and it reflects a certain duality among these global cohomology groups. Right. So, I mean, you can sort of take the dual of this sequence, if you like, and then replace the local cohomology groups with their duals via Tate duality, and you'll get a very similar looking sequence for T dual 1. I should say that actually there's a little more to it than this, because you actually have, if I is greater than 2, then HI G FS T is actually isomorphic to via restriction. So these are restriction maps here. VNS HI GF VT. Now I should say, if you look at this duality here, this is telling you that the local groups have cohomological dimension 2. They vanish in cohomological dimension greater than 2. So you might ask, because 3 would correspond to H minus 1. So why do I have this? That's for the real places, because the real places don't vanish. They have infinite cohomological dimension. So this is just really sum over the real places. Okay. And of course that'll vanish unless P is 2. Okay, so one way of phrasing Poitou-Tate duality is that if I let Shaw I GFS T be the kernel of HI GFS T going to the direct sum VNS HI GFV T, then Shaw I GFS T is dual to Shaw 3 minus I with coefficients in the Tate twist of the Pontryagin dual. So this is for all I. Okay, but actually you can sort of do a better duality than this. So there's this thing called a compactly supported cohomology, and I'm just going to define it sort of in a ad hoc way. So compactly that makes the duality kind of silly. So if I define hi lower c in parentheses, GFST to be the H3 minus I DFS. Oh, this is a bad definition. No parentheses. Yeah, this is a bad definition. So this is not the optimum definition because it oh no, it's perfect. Sorry. Okay, it is the optimum definition. Okay, so it's not really the usual one for compactly supported cohomology, but it's the optimum one. Okay. So anyway, so I define this, then obviously this is dual to well, maybe it's not so obvious. Right? Yeah.
I think it's 2 and not 3. In the duality.
No, it's 3. Oh, you mean here? Oh, here. Let's see. Right. Maybe I got this wrong. That could be right. Let's see. So.
Because in case your GS is a colloquial dimension 2, right?
Yeah.
Then H0 would be 0. No.
Right, but well, let's see. I mean, maybe we'll do an example. Yeah. So. Yeah, I'm not sure. Let's. So what are you saying? If I is.
If you define your compactly support something, or even for the SHA.
Right, for the compactly supported, it's definitely right. So what I want to claim is that.
Think of cohomology and no, it doesn't need 2 minutes.
No, I mean, so compactly supported cohomology groups are supposed to vanish in dimension 0. Yeah. What about the SHA? Yeah. So, right, let's do an example. So if we take ZP1 coefficients, right, so what do we get? We get the kernel of EF goes to direct sum V in S FV cross P, so it's locally trivial. Okay, and SHA2 GFS QP mod ZP is the kernel of H2 GFS QP mod ZP goes to direct sum V in S H2 GFV QP mod ZP. Right, both of them should be 0. Well, I think it's
right, because your SHA 0 is always 0 by definition. Right?
yeah, should be.
Which it should be.
It should be. SHA 0 should be 0. Yeah.
Because that's the first part of this Plott sequence.
Yeah, I think this is fine. Okay. So, okay. So they should both conjecturally be 0. Yeah. By Leopold's conjecture. Yeah. Well, both of these, like.
Yeah, both of those are 0.
Oh, but this is 0. Sorry.
That is 0, yeah.
That is 0, and this one's 0. Thank you. Yeah. Okay. Anyway, so okay. So in fact, this HICGFST is the cohomology group. So the ith cohomology group of a certain complex. Okay, so this complex is defined as some sort of cone of some morphism, but let's just take it to be this complex fits in an exact sequence that's non-split of the form GFVT, and then here is some shift of the degree. This is just sort of an aside. And here I need to take Tate cochains. And then goes to this compactly supported cochains, and then goes to this. Okay. And it satisfies, let me just point out, HICGFST is dual to H3 minus I, and this is by the definition, right? T dual 1. So it's set up to make the duality work. Okay, so now okay. So let me do one other example. H3 compactly supported GFS ZP1 is H0 GFS QP mod ZP dual. And so that's just the dual of QP mod ZP, so that's ZP. Okay, so this is analogous to the fact, so in local cohomology, local case, V non-Archimedean, you have H2 GFV ZP1 is isomorphic to ZP that we said before. Okay, so both of these dualities, if you like, are taking place with respect to a certain cup product. So I'll explain that in a minute. But the cup product will be to this group in the global case and to this group in the local case. Okay, so actually I wanted to do one more thing because I didn't tell you what H2 was. So H2, so if we write our Poitou-Tate sequence, for ZP1, then we have 0 goes to right. 0 goes to H2 GFS QP mod ZP dual. The first two groups are obviously 0. Maybe this one isn't so obviously 0. Goes to EF. Goes to, yeah, I'm not sure that these are.
Well, the first one is Leopold, right?
The first one is Leopold, right?
Yeah.
And this one is also Leopold.
Yeah,
That's why I thought they weren't 0. Yeah. Okay.
They should be 0 by
They should both be 0 by Leopold's conjecture. Okay. And so then this thing goes to direct sum V in S, FV cross P completion, goes to what I'll call XFS, or goes to H2 GFS ZP1 goes to the sum of the Brouwer groups. So the sum V and S, H2, the peak, right, the tape modules of the Brouwer groups, if you like, that we discussed earlier. And then, so this is either ZP or Z mod 2Z, and then goes to ZP, which is this H3, goes to 0. Okay, so that's the Plott 2 Tate sequence. And so this is actually isomorphic to H2 compactly supported GFS ZP1, which, if you like, by the definition is H1 GFS QP mod ZP dual. And so now you're taking homomorphisms from GFS to QP mod ZP, so it factors through the Bilineization and the maximal pro-P quotient. And so this is actually, the.
Did you say what XFS was?
Yeah, it's defined by this, what I'm describing now. Yeah, so XFS, I'll write it. So XFS is the Galois group of the maximal abelian pro-P unramified outside P extension, S extension. So in other words, it's the maximal abelian pro-P quotient of GFS. And that's what this is, right? Because this is GFS, right? This has to factor through the pro-P quotient because it's going to QP mod ZP, and it has to factor through the Bilineization because it's going to an abelian group. So I'm taking the double dual of XFS. Okay, so we have this sequence, and now I think, unfortunately, I want to erase this bottom part here. Right. Okay, so let me just, sorry about that. I'm going to erase this. So now if you look via class field theory, these can be identified with the decomposition groups at primes in V. And now those are mapping to here into the decomposition groups in this group. So the co-kernel of this sum going to XFS is the maximal quotient, which is completely split at all the primes in S. Okay, so that's, let me call that XFS, and then it injects here. So XFS is the Galois group of the maximal unramified abelian, actually now P extension, but I could write pro-P extension. Pro-P, I guess in the case that it's a function field, it might be pro-P. Pro-P extension of F completely split at V and S. So this thing I'll call, again, S ramified. And let me call this ramified. And let me call this one S split, just for short. Okay. So now you see I've described this H2 explicitly, right? Via a 4-term exact sequence. Okay. So that's the description of X2. This thing via class field theory, in the case of the number field at least, is the maximal quotient of the class group of F by the primes in S. The classes of the primes in S. The P part, yes. The P part of the class group. The elements of P power order. Okay, so now let me again explain Tate duality in terms of the cup product that I was mentioning. So we have cup products. If I have So suppose I have T and I also have A, which is either discrete or compact ZP double bracket G module. So now I'm back in the general case. Then I can consider cup products HIGT cross HJGA to, so I need now a pairing. So to HI plus J, G something else, let me call it L. So for some phi, which is a bilinear, ZP bilinear pairing, that's Galois equivariant. Okay, so if I have maybe tensor product. Right. Right, so Galois, so this is a map of ZPG modules where G of dot T tensor A is G T tensor G A. Okay, so if I have a pairing like this where L is some other discrete or compact ZPG module, then I can define a cup product like this. Okay, and how does a cup product go? Generally on cochains, what it does is if I have some cochain, let's say, what do I want to call it? Chi in here, or maybe chi isn't a, let me call it F in here and F prime in here. So now I'm thinking of the cocycles, some cocycles. So these are the classes of cocycles. So then the cup product is represented by the following cocycle. Imagine I have some sort of I tuple. So this is in G to the I, and this is in G to the J. Then the tuple is just, the pairing is just phi of, right. So I imagine I apply, F to this sigma, this vector of sigmas, if you like. And then I tensor that with the product of sigma 1 through sigma I. And then I apply F prime to the second tuple. And then I apply my, my pairing or my ZPG module homomorphism to that. And then that's the explicit cocycle representing the cup product. It's not so important for what we're doing. Now the point is that Tate duality actually comes from a cup product to this group here. So Tate duality comes from HIGFVT cross H2 minus I GFV T dual 1 goes to H2 GFV QP mod ZP1, right? Because there's definitely a pairing. T cross T dual 1 goes to QP mod ZP1, which is just the P power roots of unity. Okay, and this thing is QP mod ZP, so I'm assuming V is non-Archimedean. And then that's how you get this is a perfect pairing, and that's how you get the duality. Okay, between HI and H2 minus I. And similarly, Plott-Tate duality, if you take the explicit cochain complex, there is some cup product that you can make this sort of thing work. GFS T cross H3 minus I C GFS T dual 1 to H3C GFS QP mod ZP1, which similarly to what I said before for ZP is QP mod ZP. So again, it comes from some sort of cup product which can be defined explicitly on cocycles for the complex, which I didn't quite define, but almost. Okay, so, right. So an example of this is the local reciprocity map comes from this. So how does that come out? So if I take H1 GFV ZP1, and then I take the map, which takes an element A. So again, remember this was FV cross P completed, so the multiplicative group P completed. So then I take left cup product with A, or actually let me do, I think what I want is right cup product with A. Okay, so so that map goes to so where is it? Sorry. Let me just write it this way. Okay, so I wrote the wrong thing. Okay, so I'm going to take the map that's given by Poitou-Tate duality to QP mod ZP dual, right? And right, and so this thing is what? This thing is again the dual of the P completion of the Bilianization, like that. So we get double dual of that. So we get a map like this, right? And this is the reciprocity map on the P completion. So this is reciprocity map of local class field theory. So this is a maximal abelian pro-P quotient, if you like. Right. So I'll just leave it at that instead of saying what I was going to say. Okay. So okay, so let me try and do this globally. Okay, so now globally, let's suppose I want to do it globally, but to explain how it works globally, I have to explain how it works locally. So let's let xv be this this for brevity of notation. I can construct an exact sequence like this: 0 goes to xv, goes to t, goes to zp, goes to 0. And how do I construct this exact sequence other than just taking it to be split or something? So such a sequence of zp gfv modules, okay, is defined by a cocycle, right? So I need a cocycle. So what cocycle do I take? So what is the cocycle? It should be from GFV to HOM from ZP to XV. Okay, but of course this is just XV. And there's a canonical map, which is, let's take the restriction map, or a projection if you like. Right? Because XV is a quotient of GFV. Okay, so that defines naturally an extension like this. If you like, explicitly, the Galois action on T, if I think of T as consisting of pairs, right? So if I have x comma n in T, then and sigma in my Galois group, then sigma x n equals x. Yeah, so the Galois group acts by conjugation on this thing, so it's a trivial action because it's abelian. And so then I just put in the pi of sigma here. Maybe I should put times because I'm working in a multiplicative group. And then it acts trivially on both sides, but it doesn't track trivially on the extension. So we get this thing. Okay, so that's the action. Now this, if I take the GFV cohomology of this thing, I get a long exact sequence. Oh yeah, but what I said was, no, okay. So I get a long exact sequence. And the first connecting homomorphism, so first I want to twist the sequence by ZP1. So now I have a sequence 0 goes to XV1, goes to T1, goes to ZP1, goes to 0. And now if I take the long exact sequence, so the first connecting homomorphism is just a map from H1 GFV ZP1 to to H2 GFV XV1. And what is this thing? This thing is again FV cross P. And this thing, again, this Galois group acts, this has a trivial action. XV does, ZP1 doesn't, but so actually, since it's cohomological dimension 2, it turns out I can pull this out of the H2, and this thing we saw was just ZP. So this is just XV. Yeah.
Slightly confused. And this action,
yeah.
might be x times pi is q to the n or something like that, because.
Oh yeah. Thank you. Right, to the n. Thank you. Yeah. To the n. Right, so you see what now I have a map between the same two groups I had before, and I claim that this map is also, so this is also rho v p, the reciprocity map. That's maybe not so obvious. This map, what does it do? It takes A, okay, so I have an A in here, and then I need something which evaluates on, oh, that's why, right. I need something which evaluates on elements of this, so I take A cup product, so I need if I have a chi in this group, chi in this, before I take the dual, chi will get sent to the invariant map, if you like. Remember, this group is canonically, the H2 is canonically QP mod ZP. So if I take chi cup A, then that's an element of QP mod ZP. So that's what this map is. On the other hand, right, maybe I claim that this is the same thing, right? So if I follow this by some character, right? Oh yeah. So let me not try it. Oh, okay, I'll do it. Chi of rho VP of some A. So I have chi, which maps GFV to QP mod ZP. Then I have A in FV cross P. Then this thing is A cup chi, by definition, O chi cup A. And actually, what is this connecting homomorphism given by? It's given by, I'm afraid it was A cup chi here, what I wanted. No?
No, what's
One's the negative of the other.
oh.
So A cup chi, and this is actually chi applied to, so this is cup. Oh no, it was right the other way. Well, anyway, if I make them, it was right the other way. chi cup A. Okay, so if I make this, so if I imagine applying chi to the oh, I really don't want to do this. Somehow this is chi of A cup pi, and this is yeah, let me not do this. Chi of this map phi of A, something like that. Okay, so so that's how you see that they're the same if you do an argument like that. But please ignore that. Okay, so now what about GFS? Okay, so again we have this cup product, so we can do the same game. We also can create a sequence like this. Okay, so let's create a sequence like this. 0 goes to xf. Let me erase this too. 0 goes to xfs, goes to some t, goes to zp, goes to 0. Okay, so again by the same action, defined by a pi which takes from GFS and then surjects onto XF, I think S. Okay, again that's just the maximal abelian pro-P quotient. So, so then so what do I get, right? I now have a map from H1 GFS ZP1 to H2 GFS XF1. Now I can't quite do the same argument XFS as before unless, so the reason I could get this isomorphism is because GFV has cohomological dimension 2. So if I have that cohomological dimension 2, so that would be that P is odd or F no real places. Then I could get an isomorphism like this. I can pull the XFS. The action's still trivial, so I can pull it out of the H2. And now we had a description of this with a 4-term exact sequence. So, so you get a map like this. And let me call this map psi f or psi fs. And psi fs is what I'll call the S reciprocity map for f. So again, remember that this H1, so I should think of this not as a map on this, but as a map on EF or EFS. I guess I was calling it EF before. So it takes an S unit and produces an element of this tensor product. Okay, so it's a little stranger than the usual reciprocity map. So if I have a chi, actually, from a GFS to any group, for instance, let's say I have it to ZP. Oh, I think it should have been to ZP here, maybe. But anyway, suppose I have a character like that. I can imagine applying chi tensor 1 to psi fs of some A in here. So I have A in EFS. And what do you actually get? It turns out what you get is chi cup A in H2 GFS ZP1. So this thing, so the point is that it interpolates cup products. Okay. Right. So I just point out that, well, you can do all this in the context of Iwasawa theory. So really my goal was the construction of this map, okay, which I'll use in the future, though not so prominently, but I think it's really quite nice. But you can actually do all this in the level of Iwasawa theory. So if I have, let's say, for instance, F infinity over F is the cyclotomic ZP extension. So it's contained in, right, contained in F adjoin all P power roots of unity. And gamma, the Galois group, is isomorphic to ZP. You can actually define Iwasawa cohomology groups. And how are those defined? So let's say that FR over F has degree, just by my choice of preference, p to the r minus 1 for r greater than or equal to 1. So F1 is F. So the ith Iwasawa cohomology group, which to recognize the role of S, instead of, often it's written with a sub IW, I'll just put an S there. So this thing for F infinity with coefficients in some t, so t is as before, some compact module, is equal to the inverse limit of the hi GFR, and now I take the set of primes of FR above S above FR, above the ones in F, of FR above the ones in F, T. And these are under co-restriction maps, or like norm maps. Then you have these Iwasawa cohomology groups. And these become, the nice thing is that these become, these have a gamma action on them. And in fact, which is continuous. And so if we let lambda be the Iwasawa algebra, which is isomorphic to a one variable power series ring, non-canonically, then these become so lambda modules. On these cohomology groups. So often one studies these Iwasawa cohomology groups, say with the coefficients in ZP1, like the examples I gave, and some inverse limit of the S reciprocity maps gives you an S reciprocity map among Iwasawa cohomology groups. So maybe I will not discuss that now, but you can can define, maybe I'll just say what the maps are, where they're from. So can define psi maybe F infinity S from the inverse limit of the FR S's to some analogously defined thing over the level of F infinity, and then tensor some Iwasawa cohomology group with an S. So you can also do this. So these are it takes a norm compatible sequence to an element of the maximal Galois group of the maximal and ramified outside S extension of F infinity, tensored, maybe complete, with the inverse limit of the H2s. So you can do all this stuff in the inverse limit as well. But I'll just leave it at that. Probably in the next talk, I'm going to talk not so much about Iwasawa theory, but maybe in the third talk. Thank you.
Any comments or